Okay, the last thing we're going to look at are some reactions that amines undergo. And there's actually several that we've already saw. For example, remember we took arylamines, the diazonium ion, and then we did substitution reactions with a variety of different things. Just one of the many examples. We treat this with copper cyanide and convert that to the cyano group. So that was one reaction. We did conversion of amines to amides. And we did that by reacting with a more reactive carboxylic acid derivative. Like an acid halide, for example, if we react that with ammonia, we can get the amide. And then we also took amines plus aldehydes and ketones and made amines and enamines. Just one review example for that. Benzaldehyde, and for this we'll just keep it simple and use ammonia as our amine. Here we get an imine. So those are a few of the things we've already done with amines. Now we're going to look at an elimination reaction. But first, I want you just to recall the E2 elimination from Organic 1. So in an E2 elimination, what we do is we take our base, just abbreviate that as B minus, then we have some organic molecule with a leaving group, things like chloride, bromide, iodide, tosylates, things like that. And what you did is you labeled the carbon with a leaving group as alpha, the next carbon over is beta, and as long as you have a beta hydrogen, the base will grab the beta hydrogen, send those electrons down between the alpha-beta bonds, and you lose your leaving group. And the net result is we end up with this alkene product. But when talking about this reaction, you probably remember that we said we can't do this with NH2. So the leaving group cannot equal NH2 because it's a terrible leaving group. So what then can we do to make nitrogen a better leaving group in order to be able to get an E2 type elimination? We can do this through a specialized type process known as the Hofmann elimination. Now, when talking about elimination in Organic 1, we talked about Hofmann products and Zaitsev products, where Zaitsev gave us the most substituted double bond, Hofmann the least substituted double bond. Now, while this elimination we're going to talk about is specialized conditions, this is really where that name comes from, because we're going to find that when there's an option, we actually end up with the least substituted double bond. So basically what we're doing in this Hofmann elimination, the whole key here, it makes nitrogen a better leaving group. So for example, let's say we have this amine, and we're going to subject it to the following 3 steps. We're going to use excess iodomethane, silver oxide, and water, and then we'll heat it up. Okay, if we think of the nitrogen as our leaving group, it's on the alpha carbon, here's the beta carbon, and we of course have a beta hydrogen. So we're going to lose our nitrogen leaving group and beta hydrogen, and end up with this alkene product. Then our byproducts are this trimethylamine, water, and silver iodide. So we need to go through the steps here, each of these 3 reactions, and see what's happening in order to get this elimination process to occur. So starting with step 1, this is just a nitrogen alkylation, which we saw when talking about preparing amines. Okay, so here's our molecule. I'm not going to draw the hydrogen in this time, the beta hydrogen. Here's iodomethane, just like we saw before an SN2 reaction. And then, just like before, a base can take one of these protons. Leaving us with going from the primary to a secondary amine. Well, then this will just happen again. We won't go through all the steps, but now we get the tertiary amine. And then it can happen one more time. And we get this ammonium salt. The second part of this reaction comes where we add the silver oxide and water. So let's take our ammonium salt. just going to abbreviate my 3 methyls. And we react this silver oxide and water. So this step we're going to call an ion swap. Because what actually happens is the silver oxide and water is generating hydroxide, and the silver will pair up with the I minus, take that and form silver iodide precipitate. So it gets rid of the I minus and replaces it with OH minus. So there's our new ion. And finally, step 3 is heating. And by heating, we eliminate. Okay, I'm going to go ahead and draw back in our beta hydrogen. But what you should notice is that we have this positively charged nitrogen species, which is, unlike a neutral nitrogen, a good leaving group. We also have the hydroxide paired up with it. Remember from Organic 1, heat favors elimination. So by heating this up, the hydroxide will act as a base, grab the beta hydrogen, and eliminate. There's the alkene product, plus water, and trimethylamine. Now in this case, it was pretty straightforward because there was only one type of beta hydrogen to eliminate. But if we have multiple types of beta hydrogen, we can potentially get multiple products. Now remembering the name Hofmann elimination, if multiple products can form, the product that has the least substituted double bond will be the major product. Okay, so let's look at another example. Okay, so here we have our alpha carbon, which has a nitrogen attached. But we end up with 2 different beta carbons that each have beta hydrogen. So we have 2 different types of beta hydrogen here. Now under the Hofmann elimination conditions, excess iodomethane, silver oxide and water, and heat, If we eliminate through, we'll just say beta hydrogen type 1, if we eliminate through that beta hydrogen, we're going to end up with this alkene. Okay, and potentially, depending on the stereochemistry you start with, potentially the cis or the trans isomer. Okay, but if instead we go through, say, beta hydrogen type 2, if we eliminate across that alpha-beta bond, we would get this product. So now what you can look at is the double bond substitution. Beta hydrogen 1 gives you di-substituted alkenes. Beta hydrogen 2 gives you a mono-substituted alkene. So that's a preferred pathway, and this is the major product. So just like the Hofmann products in Organic 1 that we talked about that were the least substituted double bonds, that's what the Hofmann elimination gives. The easiest way to think about why this is, just think about the fact that once you alkylate the nitrogen, you get the nitrogen with 3 methyl groups on it. And those methyl groups are pretty good size. And basically what it comes down to is this hydrogen that leads to the less substituted double bond is sterically easier for the base to get to than the other beta hydrogen. So we'll just say due to the bulky leaving group, the trimethylamine, it's just easier for the base to grab this more accessible hydrogen. Okay, let's look at one final example where we have a cyclic amine that we're going to send through a round of Hofmann elimination. We'll find your beta carbons that have beta hydrogen. Actually have 3 beta carbons here, but the one that will end up giving us the least substituted double bond is this one. So we're going to eliminate across this alpha beta bond, and we'll lose the nitrogen as the leaving group. So if it helps, you can always draw out your intermediate structure. So here we end up with 2 methyl groups on the nitrogen. We're going to eliminate from this beta hydrogen. Break that open. The one difference here is your nitrogen leaving group is still, because it's cyclized, it's still going to be attached to the molecule. So we get this alkene. And this is as far as this will go, unless you subject it to a whole second round. Meaning you have to do all 3 steps one more time. Okay, this isn't something that just automatically happens. You have to make the choice to add those reagents a second time to do this. In that case, here's your alpha-beta bond. And that's your only option here. So when this undergoes the Hofmann elimination, we end up with, in this case, this diene. And the trimethylamine does come off this time.